Good morning. Okay, today I'm going to discuss common source amplifier with RS. RS is nothing but degenerative resistance or negative feedback resistance. Let us see how it acts as negative feedback resistance. Now, this is a circuit diagram of common source amplifier with degenerative resistance RS. Now, I'm going to explain how it acts as common source and degenerative resistance. VI is applied to the gate and output is taken from the drain, so that which is the common terminal, so hence it is called as common source amplifier. That is okay. Next, I connected the resistance RS in the source terminal. This is okay. This resistance acts as degenerative resistance, or we can say that negative feedback. Very simple. Okay, if V naught or V naught changes due to the change in the MOSFET or temperature, any other reasons, okay, it will provide the feedback from output to input. Hence, it is called as degenerative resistance. And the factor which is okay going to provide always here 1 plus. That all of you should remember 1 plus. The resistance looking at the source. Here once again the resistance RS is there. We need to consider the resistance here, that is GM plus GMB. Always you should remember, whenever the resistance at the source terminal, the body and source force in not be in the same potential level, the resistance we have to consider is 1 plus GM plus GM plus GMB, so that you'll get GM 1 plus GM plus GMB, okay, plus into GMB into RS. This is the degenerative factor. Always we are going use degenerative factor because of the RS. This degenerative factor is very important. Now, because of the RS, the body, this is the body and source are not in the same potential level, so that we need to consider body effect. Now I'll go to the next slide. Okay, you can see here I'm going to write AC circuit. Whenever I am writing the AC circuit, remove the current source I and connect the load RL. I connected here. Okay, applied voltage VI will be converting into current. Okay, that current we'll see afterwards. What is the current which is producing? Now the body and source are not in the same potential level, so that I considered the resistance at the source is 1 over GM plus GMB. Now, input resistance R in equal to infinite. Very simple. IG equal to 0. Even VI applied, IG is 0, so that VI by IG is 0 is infinite. Input resistance is infinite. Now we have to calculate output resistance. Whenever you are calculating the output resistance, you know that RL will be removed. R out equal to, easily you can remember this expression, R out equal to this resistance R naught. Okay, I written the R naught now, R naught, and the factor which is going to add up is 1 plus GM plus GMB into R naught into RS, that is due to negative feedback. Okay, this is the resistance is adding. It means that the resistance gets increases. GM plus GMB into R naught is greater than 1, so that we'll get like this. So you can write it R naught. See, very simple. R naught plus GMB into RS is the negative feedback factor. You have to multiply with R naught. So that final expression is this one. Okay, R naught into 1 plus GMB into RS. This is the output resistance of common source amplifier with feedback. Sorry, with RS. Next, I move to the next slide. Open circuit voltage gain. In order to calculate open circuit voltage gain, I have to remove the load. Once I remove the load, current will become 0 at the drain terminal. The current at the drain terminal is 0. Whatever the current at the source, that is also 0. So that this is also 0, so that the source is virtually grounded. I mean that now VGS equal to VBS. Okay, VGS equal to VI, so VBS is 0 because body is already grounded, source is already grounded, so that VBS is 0. Now V0 by VI you have to calculate. Now applied voltage will be converting into current. That current is called as GM into VGS or GM into VI. Now, okay, that GM into VI is very simple. Which direction it is moving? Okay, you have to identify. VI is applied here. This is the positive. Correct? Source is negative. This is the VI. So that current entering is positive, leaving is negative. So that it is moving down. In the previous case, common gate is moving up. Now it is moving down because current entering is positive, leaving is negative. So that it is moving. It is converting into current called as GM into VI. Now that current will come to this node, and the current flowing through the RS is 0. It has to take the path through the R0. This direction is very important. Now current entering is positive, leaving is negative. So that, okay, V0 is dropped like this, plus and minus. This is the V0 direction. The drop across R0 and V0 are opposite. So that V0 equal to minus I into R0. I is GM into VGS. VGS is same as VI. So that we can write that AV0 equal to V0 by VI minus GM into R0. That is nothing but intrinsic gain. Because, okay, no external components are there. Only MOSFET alone will be there. So that we need to consider only intrinsic gain minus GM into R0. Now I'm going to represent equivalent circuit. Okay, equivalent circuit of common source amplifier. Okay, okay. By you see here, you know that V0 by VA equal to AV0. Okay, AV0 or minus A0. So that V0 equal to minus A0 into VI is the voltage source. So voltage source plus and minus, it will have the resistance in series, that is R out, that you have to calculate in the next slide. Next it is RL. Now overall gain I have to calculate. Let me move to the next slide to calculate overall gain. Okay, not overall gain, short circuit transconductance. In order to calculate short circuit transconductance, GM equal to AV0 by R out. Very simple. This is the current gain. This is the voltage gain. So that R out you have to remove. Okay, R out you have to divide it with. So current short circuit current gain GM equal to voltage gain AV0 divided by R out. So AV0, you know that GM into R0. R out we calculated this expression. So that R0 in the numerator, R0 in the denominator get cancelled. Finally we'll get GM divided by 1 plus GM plus GMP into RS. See, whenever RS is connecting, the the transconductance is divided with the degenerative factor. See, degenerative factor, output resistance increases, the gain decreases. This is very important. The effect of RS reduces GM, but R out is increased by this much. Now I am going to represent in terms of transconductance. Okay, you can represent GM is the current source, GM into VI is the current source, and it will have the resistance in parallel, that is R out. I'm converting, okay, Thevenin's equivalent circuit into Norton's, so that we'll get like this, and RL, okay, always the GM will be divided with the negative feedback factor, degenerative factor. Next I'll move to the next slide. Okay, voltage gain with RL. In order to calculate with voltage gain with RL, V0 is the this voltage, and applied voltage is A0 in minus A0 into VI into RL divided by RL plus R out is the voltage divider rule. So that AV equal to V0 by VI, that is equal to minus AV0 into RL divided by RL plus R out. Now, okay, the voltage between gate to source equal to VI divided by negative feedback factor 1 plus GM plus GMB, always because RS is used to control the VGS within the linear range, so that it will produce the okay, in linear range only, but it reduces the VGS, but it expense of gain. Okay, this is the end of common source amplifier. Thank you. Any doubt?